Prions. The only disease we know about that doesn't involve genes. It's only involving sort of misfolding of proteins, which can lead to infection. So to get infection, you have to be able to have those prions do one other thing, and that's split. You have to have fission, and then like nuclear fission, then those prions can have a runaway growth, because as soon as you get little pieces of this crystal starting to split, then those can run off and start to grow elsewhere and split, and those can run off and start to grow elsewhere and split. When you get the disease, it's very brutal because it just eats away your brain. The prions aren't the only one of these kinds of situations where proteins run wild. It's also true that bacteria and viruses, of course, replicate and grow. But as an infectious protein disease that has this runaway growth, this is it. Alzheimer's disease is another famous example where the proteins will also fold into a form that allows them to grow into these crystals. But Alzheimer's, unlike prion diseases, Alzheimer's is not infectious. Unlike any other disease involving infectious units, they survive to high temperatures. They survive to high ultraviolet exposure. They survive under things that would just blast the bejesus out of bacteria or viruses. The two places where you're guaranteed to find a fair number of them is on the surface of neurons, and that means any neuron, neurons that run down your legs, neurons in your central nervous system of your brain, and you'll also find them in the lymph system. There's some evidence of them being expressed in urine of mice and in sheep's milk, and that's probably important to how the prions can spread when you take them in digestively, that they first probably go to the lymph system and then they can make a transition there from the lymph system to your neurons. One thinks of prions as being sort of evil, but that's another interesting direction to go in, is to think, how could I use these things to make some interesting new materials that would be inspired by these biological counterparts? There's a fellow at the University of Delaware who's actually growing amyloid proteins as scaffolding to grow tissue. And spider silk actually contain pieces of amyloid protein that contribute to the remarkable ductile strength of spider silk, which is stronger than steel. And there have also been people who have used the actual the amyloid fibrils themselves, which are these one-dimensional crystals formed out of these proteins, as a way to grow wires. And one group has grown wires on the outside of these things, and another group has figured out how to grow metal wires on the inside of these things. And those tiny wires could be useful in nanotechnology. So you can imagine using these things to template growth of various novel materials on the nanometer scale, or to design materials where their tough structure is built in, much in the way that it's built in apparently in spider silk.